And that was just a rough guess. It started with an atomic guess. But then it calculates the energy, if that's where the electrons are, and then it calculates the density from the energy, and you get a different density. And then it says, oh, let's use the density I just calculated as a better guess to the density, and then it cycles, and the energy keeps going down and down and down until the energy comes down no more, and then it says I've got the electron density. And so what you see here is that electron density plotted. And running across the top here, does this work? These are the molecular orbitals. And the top line is the energy of those orbitals. The next line, the 1, means you're in shell 1. Shell 1 has 2 electrons in every orbital. And shell V, or virtual, has no electrons in every orbital. So you see orbital 62 here is the HOMO orbital, the highest occupied molecular orbital. And orbital 63 is the LUMO, the lowest unoccupied molecular orbital. So the molecule is put in the XY plane. So if you look down lower, you see atom 1 here, and atom 1 is on the phenyl ring. It's this atom here on the phenyl ring, that's 1. Here's atom 2 on the phenyl ring. So if you look here, it says that this PZ orbital on atom 1 has a weight of 0.36 in orbital 61. And that's then plotted on these figures down here. We come to orbital 61, which is this orbital. The 0.36 is that one there. And down lower here, the 0.54 is that one there, a little bit bigger. So that's how the output of the program gets put onto the visualizations that you've seen in a lot of the lectures during the week. It's telling you which orbital on which atom is appearing in the molecular orbital at that energy. Does that make sense to everyone? And all these orbitals have pi symmetry. The A double primed up the top there means it's pi symmetry, although 57 here is A prime, that's a sigma orbital. But we're only looking at the pi orbitals, and we're assuming the molecule is flat, which won't be true in reality, but it's a good enough assumption for us to hear today. So, then given you a plot here of the most important orbitals, and those orbitals, some of them are on the phenyl ring. For example, this orbital here is the LUMO orbital on the phenyl ring. And if you come up to here, that's the same orbital on the quinone. So, same shape orbital here and here. Now, other orbitals change shape. So, what we're asking you here is, when you change the chemistry from a benzenoid molecule like the phenyl ring to a quinonoid molecule like the tetracyanone NQ, what's the N stand for? Q is quinone. The electronic structure changes quite a lot, and that change in electronic structure tells you why quinones are good electron acceptors and why they're very commonly used through nature and in artificial devices as electron acceptors. The next page here, sorry that turned out like that. You might want to share 2 copies of the printout with the person next door to you so that the 2 diagrams are on the same page. So here, you're asked just to sketch the basic form of the orbitals. So this here, orbital 60, if you look at the previous page before, orbital 60 has black on one side, white on the other side, and 0 in the middle, which is a nodal plane running through the middle. So here, you've drawn the 2 black, the 2 white, and the nodal plane. Oh, wonderful. Jacko never ceases to amaze me. Where's the other one? Over there. Oh, yeah.
Look what you can do.
You take that! Now, similarly, you can find this orbital here. Oh. Well, your task is to draw the other 6 orbitals from that are on the quinone part over here. And then the question is, how do these orbitals here on the phenyl ring relate to these orbitals here on the quinone? And I'll give you a clue what you're going to find. Look at this orbital here on the phenyl ring. That work? No.
Number 61?
Yeah, number 61. You see 3 black and 3 white. Now, look at the LUMO orbital, number 63. 61 is occupied, 63 is not. Look at orbital 63. Forget the bits on the end, what do you see? 3 black, 3 white. So the LUMO orbital in the quinone is an occupied orbital in the phenyl ring. So to make the quinone, you've taken 2 electrons out of an occupied orbital. Is that orbital going to be happy not to have 2 electrons in it? What do you think? Anyone going to say no? So if the orbital isn't happy, does it sit up here, where the unoccupied orbitals should sit, or does it sit in the middle of the band gap? So, benzenoid compounds have a huge band gap. They absorb in the ultraviolet. The TCNQ has an orbital in the middle of the band, an unoccupied orbital in the middle of the band. And quinoids are very popular dyestuffs. They're extremely brightly coloured, and they're extremely good electron acceptors because they have this very low energy LUMO orbital. And you can see here why the quinoid has a low energy LUMO orbital. It's ripped out of an occupied orbital in benzene. So the idea of this is to give you a feel for what orbitals are and how what happens to these orbitals control the bulk properties of the material. Like any organic chemist will tell you that the chemical reactivity of the phenyl ring, the aromatic phenyl ring, is completely different to the chemical reactivity of the quinoid here. So it's not just the colour that's completely different, everything is completely different. And it's caused by where the electrons are, and that's what the orbitals are telling you. And when you do anything in a real device, this is the sort of thing you're manipulating. So any questions people want to throw at me? No? Well, keep going.
Might be a good idea to turn off some lights. It's a little bit, dim them just a little bit. This is better, but maybe a bit more. Okay.
That's good.
Could maybe give us a light in the back?
Unfortunately,
For a bit of inspiration, that's what the answer looks like.
I'm not sure.
The orbitals on the TCNQ and what relates to what.
Do you know anything about molecular orbitals?
Molecular. That's it. You didn't learn it?
I learned it. I learned it like 7 years ago.
It's nothing else. It's still like
No, I mean, I know